Hi everyone, welcome to our video on finding concavity and inflection points where we have this natural log function that's involved. Alright, so in our previous video we broke it down with a polynomial. It's the same steps, we're going to break these down, it's just a different function. Alright, so and whenever you have concavity, I'd still think of those people right there. I'm just going to put them in the corner for now, just to remind yourself, if you ever see concavity or inflection, these two are going to be helpful for you. All right, so our first step, though, in these problems is to find the domain. Well, the domain in this scenario, the x squared and the x squared are no problem. They're no big deal at all. It's the natural log that has the problem. So the domain of ln of x is to take that x and make sure it stays greater than 0. And that's it. So, but in interval notation, we would write it as 0 to infinity. So that's our domain. So we'll keep that in mind when we do our number line. Okay, but then moving on to the bulk of the problem, we have our second step is to find the second derivative. Well, first thing we need is the first derivative. All right, so to do that, notice I do have a product with this one right there. So I'm going to use our product rule. Now, instead of writing my u and v like normal, I'm just going to go ahead and let's say it in words and plug in as we go. So the derivative, so that is u and that is v at least. I could write that. So I know it's the derivative of u, which would be 10x times just v, which is natural log of x, plus just u, 5x squared, times the derivative of the natural log of x, which would be 1 over x. And then minus the derivative of this, which would be minus 24x. All right, and then let's continue simplifying. So g prime of x is 10x natural log of x. This simplifies, so the x squared and the x reduce to just being x. So this would be plus 5x, and then we have minus 24x. Okay, and so here we see we've got like terms now. So g prime of x is 10x natural log of x minus 19x. All right, so this is our derivative, but we need the second derivative because it's concavity. So let's keep going. So our g double prime of x, our second derivative, well, this is still using the product rule. So that this is, let me just mark it. I'll put it in red to show that this is the u and the v. All right, and to save some space and time, let's word it and plug it in as we go. So it's the derivative of u, which would be 10, times the natural log of x, plus the first one, the u, 10x, times the derivative of the v, which was 1 over x. And then minus the 19x derivative, which would be minus 19. All right, and then, well, it simplifies again. Notice this x and that 1 over x would reduce. So I have just 10 left over there. So g double prime of x is, this is now just 10 natural log of x. This became just plus 10, and this is minus 19. So 10 minus 19, we've finally got it. Our g double prime is 10 natural log of x minus 9. Okay, so this is our derivative. So I'm going to cloud it. There we go, our second derivative. Okay, so that was the long step there. And then now our next step is to find the critical numbers, which is to set the derivative, second derivative, equal to 0. So we have 10 natural log of x minus 9. And then, well, to solve this, we would probably add the 9 over. So we'd have 9 is equal to 10 natural log of x. And then we should divide the 10 first now. Divide by 10, divide by 10. So we have 9/10 is equal to the natural log of x. And then to isolate the x, or to solve for x, once we have just the natural log of x by itself, is where we use e. And so we have e to the 9/10 would be, these just kind of cancel and you're left with x. So we have e to the 9/10 is x. Okay, so that is our critical number. So we found it. Okay, and then now our next step is the number line. Let's put it on this half of the page. So we have our number line. And there's only one value to put, but we also have to think about the domain. So the domain starts at 0, so I'm going to put 0 here. E to a power is positive, so I know it is to the right of 0. And then I know nothing is happening left of 0 in this problem based on the domain. And again, we'll plug it into the calculator to really verify at the end. Okay, so now that I have this set up, this misscribbling maybe kind of messed up my F and F double prime, or I guess technically G, so I usually label it, let's put it on the right though. So G double prime and G, and then these guys, I put those in a good spot. Here they are. So those tell us, this tells us the sign of the derivative, and then this tells us the concavity of that G. All right, and then these are X values that we have plotted on our number line. Okay, so at this point, I want to choose anything bigger than e to the 9/10. Well, again, e is about 3. So to play it safe, I'm going to do g double prime of 10. That should be bigger than e to the 9/10. So g double prime of 10, that's where I look back at my clouded second derivative function, and I would want to plug in the 10. So I have 10 natural log 10 minus 9. And then, well, with a calculator, we could really verify 10 natural log of 10 is going to be bigger than 9. So when this does subtract, it will be positive. Okay, so this will be positive. And I'm just skipping the calculator work. It's definitely positive. You could verify with a calculator. So this will be positive right here. And then I want to choose something that's less than e to the 9/10, but bigger than 0. So I want to plug in, I would choose something that's close to 0, like 0.01, something like that. So that's definitely bigger than 0, and definitely in between. Since e again is about 3, I'm going to play it extra safe to be close to 0. And then I want to still plug it into my starred clouded equation here. So that would give us 10 natural log of 0.01 minus 9. Well, what would happen with this, the natural log of 0.01 is a negative number. Minus 9 would still be negative. Okay, so if the natural log of 1 is 0, so anything less than 1 would give us a natural log of a negative number. So it would be true. Again, you could just plug it into a calculator to really verify. I'm just saving that one step. Okay, so this is negative there. And then now we have the concavity. So where the second derivative is negative, I have concave down, or it looks like a frown. And then where the second derivative is positive, I have concave up, which makes it look like a cup. Concave up. Okay, so there it all is, and this was part of step 5, doing this work on the number line. The final part of step 5 is to state where it is concave down and concave up. So it's concave down on this interval from 0 to e to the 9/10, and it's always parentheses on concavity. And then it's concave up on the interval e to the 9/10, comma, infinity. There we go. So there's the concavity. And then looking back one more time, since it did change concavity, concave down to concave up, I do know that there'll be an inflection point here. So at this x value, I know there's an inflection point because it changed concavity. And so that means I need to plug that in. So our inflection point, abbreviated, is to plug this x value into our original function. So g of e to the 9/10 needs to be found. And so when I plug it into this function, it looks like, let's put it over here, g of e to the 9/10 is 5 times e to the 9/10 getting squared, natural log of e to the 9/10 minus 12 e to the 9/10 squared. All right, and chances are they'd want a decimal anyway, but let's show how to break this down by hand. So the 5 is fine. The e to the 9/10 squared would have these two multiplied. 9/10 times 2 would become 9/5. So this is, and let me get rid of those parentheses. Let's just write it as e to the 9/5. So when those multiply, that's what that power would become. And then the natural log of e to the 9/10, well, a natural log and e just cancel each other out, and you're left with just that power. So it is just going to be times 9/10. And then we have minus 12. Just like before, those powers would multiply. So 9/10 times 2 would become 9/5. So it's e to the 9/5. And so it looks like we do have like terms. Okay, so this becomes the 5 and 9/10 would multiply. And we would have, eventually, so the 5 and the 10 reduce to be 1 and 2. So it would become 9/2. So 9/2 e to the 9/5 minus 12 e to the 9/5. And then at this point, we can get a common denominator. Okay, so that means the 12 would need to get multiplied by 2 on both the top and bottom. And then we'd have 9 minus 24, which would be 15, or negative 15, I mean. Negative 15/2 e to the 9/5. So if they said they wanted it in terms of e, that's how this would get broken down. So chances are I would think that they don't want it, but our inflection point, so we use this to plug it in. I'm going to write our answer right here so I don't go too much into that other one. But we have that as our x-coordinate, the e to the 9/10 is the x-coordinate, comma, and then we just found the y-coordinate, negative 15/2 e to the 9/5. Okay, so now let's use a calculator. Let's use our graphing calculator to verify and to see it. Okay, so I've got, let me exit that, and then we'll clear that. Let's get a new one. Okay, so I want to plug in that function, the 5x squared times the natural log of x minus 12x squared. Okay, and notice there's nothing left of 0. Nothing left of it. So that's what we said was in the domain. And then now I just scrolled out a bunch to see all of it, and it looks like this. Okay, so what I probably would want to do is let's change our x-axis a little bit. Let's just go from 0 to, I don't know, 100. Is that going to show everything? Looks like I'm missing some parts now. So it went too far. There we go. So I had to scroll a little bit further back. Okay, so that's what this looks like here. Okay, and they said, so it looks like it's almost concave up everywhere. Let's check our number line. So that's where the graph might be misleading. So let's check that number line. Okay, so there's the number line portion. Let me put it down at the bottom of this so we can see them at the same time. Okay, so there's the number line to it. All right, and it says it's concave down from 0 to e to the 9/10. So that doesn't go very far. So it does look like it does start off concave down. And then somewhere around here, it changes concavity to concave up. Okay, so where it changes is at the inflection point. Let's go ahead and plug that inflection point in. So it's e to the 9/10. So I'm just going to type that in, and let's see if it is a point that's going to be on our curve. So e to the 9 divided by 10, comma, not there, let's keep scrolling. There we go, not period, comma, and then negative 15th divided by 2, e to the 9 divided by 5. Okay, oops, and let's scroll over a little bit more to make it an actual point. There it is. Okay, so that looks like it, right? So that is where it's concave down. It starts off concave down, and then at this point, which is a decimal, is the negative 45.372. So this is in terms of e that I'm currently highlighting. But if you wrote it like this, that's probably fine, as long as they don't tell you to write it in terms of e. If they told you to write it in terms of e, then we have to do it the long way. If they did not, well then, that's this point instead, which we could have done with the calculator earlier. Okay, anyway, so we can see it's concave down, and then at this point, it sure does look like it's now concave up afterwards. So it looks like everything's good. Okay, so here's using calculus to verify that this is the point. On this calculator, it didn't really show it exactly, or it doesn't give you that nice point. It does tell you where minimum is. There's the relative minimum. Again, it tells you where your x-intercepts are. But other than that, nothing else. Okay, so, and 0, 0 actually is not a point. So that's mislabeled. So sometimes the calculator doesn't do things correctly. Okay, so, but anyway, so that's all. So if you have any questions, so we did find everything. Everything's good. So those 2 boxes are the answers. If you do have any questions, please let me know. Otherwise, thanks for watching, and I'll see you again soon.